Good morning, students. I welcome you all for the class. Today we are going to discuss regarding contiguous memory allocation. Right? So in the last class we have seen regarding the basic introduction to memory management. Like yesterday we have seen what do you mean by a memory and what is a memory management and what are the why we are going for different types of memory even though we are having this primary memory and secondary memory, and what are the advantages of it and what are the criteria for a computer. So everything we have seen in the previous class, and also we have seen the basic important concept called swapping. So what do you mean by a swapping? Like as the main memory cannot accommodate enough number of processes, what we are doing is we are storing all our processes onto the secondary memory. Whenever the CPU is in require of any particular process, that process we are getting from secondary memory to the main memory. So getting the required processes from the secondary memory to the main memory, we call it as a swap in. And in order to have a space for that particular process, we are deleting a particular process in the main memory. So deleting in the sense we are keeping back onto the secondary memory. So picking up the process from the main memory and dumping in the secondary memory, we call it as a swap out. So together swap in and swap out process, we call it as a swapping concept. Fine. That also can be called as roll in and roll out. So that's all for yesterday. And today we'll be going to discuss regarding one of the important concept in the memory management, and in which your syllabi cause is the contiguous memory allocation. And we will be also seeing that what are the different allocation algorithms, like memory allocation algorithms are there in order to allocate a particular process. That algorithms also we will be going to see. So we'll be going to see the contiguous memory allocation as well as the memory allocation algorithms. So what do you, as we have seen regarding this memory management, right? So memory management is nothing but a function responsible for allocating, managing a computer's main memory. That we call it as a this memory management. So what the function of this memory management is, it keeps track of all the processes, all the memory locations, keeps tracks of all the status of memory locations, like how many memory locations are allocated, how many memory locations are free, how many memory locations have not been allocated. So all the information it is going to store. That is the memory management function. So it keeps track of all the status of each memory location. So how many memory locations are there, irrespective of number of memory location, it keeps track of all the memory locations, either allocated or free, to ensure effective use of primary memory. Like how many allocated and how many free are there, in the sense, suppose if five spaces are free and two processes are waiting, if we are known that number before, five spaces are free, in the sense we can accommodate the two processes which are waiting. If we don't know the number, we can't accommodate the process. So in order to know in advance, in order to be effective in much more convenient way to the processor, like we are going to have the memory management. So it keeps track of each and every particular memory location. So that is the memory management. So there are two memory management techniques. Majorly there are two memory management techniques. The first one is the here we'll be going to see the contiguous memory allocation and non-contiguous memory allocation. So these are the two main memory management techniques, and you are going only with this contiguous memory allocation, which we are going to cover in your syllabus. Fine. In your syllabus, non-contiguous memory allocation was not there, but I'll tell you in brief what is non-contiguous memory allocation and what are the difference between contiguous and non-contiguous memory allocation. Also we'll be going to see in our further more stages. Fine. So these are the two memory management techniques, contiguous and non-contiguous. What do you mean by contiguous and what do you mean by non-contiguous memory allocation? So suppose here So here we'll be going to discuss with the memory memory management. Fine. Memory management, it's part 2. Fine. Today in this class we'll be going to discuss regarding this contiguous memory allocation. Contiguous memory allocation. So actually this memory management has been divided into two techniques. The first one is the contiguous and next one is the non-contiguous. Fine. What do you mean by contiguous and non-contiguous? Suppose for example, if you've seen this block diagram, if they've seen this, so this is the main memory. Fine. And here there are two processes, process P1 and here we are going to have process P2. Fine. There are two processes P1 and P2. So when we are going to have this contiguous and non-contiguous memory allocation, this memory has been partitioned. First of all, memory has been partitioned. So in this partitioned memory we are going to place the processes onto the memory. What memory management will do, it keeps track of how many empty slots are there and how many full slots are there. Empty slots are there and full slots are there. Here this one, this one and this one are empty slots. Suppose if P1 is there, so P1 is going to have suppose P1 can accommodate 5 instructions. 5 instructions in the sense compulsory 5 continuous allocations should be there. Fine. So then only we can accommodate P1 to this slot. Suppose if suppose this is contiguous, this whole slot is going to be allocated to the P1 process and this whole slot is being allocated to the P2 process. Suppose if P1 is having 6 instructions, but my partition is of only 5. My partition can accommodate only 5 instructions. So P1 is of 6 instruction. Non-contiguous in the sense, suppose here P1 means 5, here it will allocate and here also one empty space is there na, here the 6th instruction will allocate. This is non-contiguous. So non-contiguous in the sense, wherever we'll find the space, we'll be going to allocate the process over there. So here this is the main memory. So I'm taking this non-contiguous memory allocation. Fine. So here if a P1 process needs 2 instructions, so each capacity of 1 KB, suppose for each capacity is of 1 KB. So P1 needs 2 KB of space. Here only 1 KB, but the next is filled. These are filled. This is also filled, already occupied. So these are the empty spaces. So these are empty. So this is empty and this is empty slot. Holes, we call it as a holes. Fine. So here P1 needs 2 KB of memory, but here only 1 KB it can occupy and remaining 1 KB here it will be going to occupy. So here 1 KB it is taking place and here 1 KB we are keeping. This is the non-contiguous memory allocation. But whereas coming to this contiguous memory allocation, we shouldn't keep like this. So if P1 needs 2 KB of space, it will be searching where 2 KB of space is available. Continuously the whole thing should be allocated for P1 only. Here some 1 KB and another space, phrase space another KB. We shouldn't allocate like that. So that is the difference between contiguous and non-contiguous. I think you got the concept. Fine. Contiguous in the sense continuously, like continuously one particular slot is given for the whole process. Non-contiguous in the sense, if the space is not sufficient, we can give another space whichever it is free. Like that we call it as a non-contiguous memory allocation. Fine. So that is the difference between contiguous and non-contiguous memory allocation. So whenever we are going to talk regarding this contiguous and non-contiguous memory allocation, here you can find many of the differences between this contiguous and non-contiguous memory allocation. Contiguous memory allocation allocates consecutive blocks of memory. As I have said you, so this is the main memory, and here this is for the non-contiguous memory. So here we will be going to have like this. The memory has been partitioned. So here also the memory has been partitioned. Suppose if P1 process is there, P1 requires 2 KB of space, in the sense it will check where 2 KB is available. Suppose here this 2 KB is available. So here we will be going to allocate 2 KB of data. So that is contiguous memory allocation. Non-contiguous memory allocation separates blocks of memory to a file of process. Here non-contiguous memory allocation, if P1 needs 2 KB, in the sense here 1 KB we can allocate. Suppose if this is fill, means another 1 KB here we can allocate. What I mean to say is, here continuously in a sequence order we have to allocate. Here there is no such sort of restriction. So that is the major difference between the contiguous and non-contiguous. Faster in execution. Why faster in execution? In the sense, suppose if I want to execute P1, in the sense all the P1 instructions are there at a same particular place, so that from starting from that block, ending from that block, I can execute it in a faster. But when it comes here, slower in execution. Why? In the sense, here 1 KB is there, again I have to search where the another KB is there. So searching takes a major role. So why another KB is there? In the sense, here you will be going to have the searching is going to be late. Here the searching is faster, in execution is going to be more. It is easier for the OS to control. Why? Because at once all the data is going to be present, so operating system, it is easy. But here it has to translate where that addresses are there, and it has to translate that, and it has to fetch the data. So that is, the operating system is going to be complex over here. So overhead is minimum. Why? Because everything at one place. Overhead is maximum in non-contiguous memory allocation. Why? Because we will be going to have the data in different parts of the memory. Internal fragmentation occurs in contiguous memory allocation. This internal fragmentation and external fragmentation is very, very important. So let me tell you clearly, what do you mean by internal fragmentation and what do you mean by external fragmentation. Fine. So internal fragmentation, in the sense, suppose this is the memory. Suppose this is the memory, right? I am telling about internal fragmentation. So internal fragmentation, in the sense, as I have said you before, the memory has been divided into partitions. So this is the main memory. So internal fragmentation, in the sense, suppose the memory has been partitioned, right? How many partitions are there? 1, 2, 3, 4, 5. So memory has been partitioned into 5 blocks. Fine. Suppose if process P1, suppose here this partition is filled, for example, and this partition is also filled. Only 2 partitions are left. Internal fragmentation, in the sense, suppose this partition size is of 5 KB, this partition size is of 12 KB, this partition size is of 2 KB. Fine. Fine. This lines indicates it is already filled by any user process. These are the empty slots. So 5 KB, 12 KB and 2 KB are the empty slots. So here this is one empty slot, this is one empty slot, this is one empty slot, and this is another empty slot. If processes, there are two processes, P1, P2 and P3. P3 requires 11 kb and P2 requires 1 kb and P1 requires, suppose P2 requires 2 kb and P1 requires 1 kb. What do you mean by internal fragmentation? In the sense, suppose now P1 requires 1 kb, so P1 will be setting over here, fine. If we don't follow any algorithm, we will be going to consider the first free block, fine. So P1, now we are going to keep P1 over here, but P1 occupies how much kb? 1 kb, but the size of this partition is 5 kb, so 5 minus 1, that is equals to 4 kb left over here, fine. And P2 requires 2 kb, but what is the size over here? 12 kb, so P2 requires 2 kb and size of this partition is 12 kb, that is 12 minus 2, that is equals to 10 kb. And P3 requires 11 kb, but here we can't accommodate P3. Why? Because here only 2 kb is left. This is how we are not following any partitioning algorithm, memory allocation algorithm. As when we follow first come first serve, this will be the happening. So P3 requires 11 kb, but here 11 kb, that much space is not available. Now this P3 will be waiting, fine. Now this P3 will be waiting. Now what is happening over here? Total how much memory is there? 12 plus 2, 14 plus 5, totally 19 kb of memory is over here. So in that 19 kb, how much memory we have been used? Only 2 plus 3 kb memory we have been used. So 3 kb memory we have been used. So what I mean to say is internal fragmentation, in the sense, here in place of 5 kb we are using only 1 kb. So this 4 kb we call it as an internal fragmentation. Internally left over fragments are nothing but leftover spaces. So fragments are nothing but leftover spaces. So internal fragmentation and external fragmentation will be there. Internal fragmentation means this one. Here P1 requires 1 kb, but we have a partition of 5 kb. So only 1 kb we are using, and how much is left? 4 kb is left. So this 4 kb is the internal fragmentation. Here 12 kb is there, but we are using only 2 kb, and 10 kb is the internal fragmentation. These are the waste of spaces. Internal fragments are nothing but, fragmentation is nothing but wasting of spaces. Internally we are wasting here 4 kb and here we are wasting 10 kb. Totally we are wasting 14 kb of memory. Fine. 14 kb of memory is going to be wasted. So this is internal fragmentation. Suppose when it comes to the external fragmentation, so when it comes to the external fragmentation, so now we will be going to see external fragmentation. So what do you mean by external fragmentation? In the sense, now here we have allocated P1, now P1 has been done, and later sometime what this P1 now some other process came, next P4 process entered, which requires 20 kb, which requires 20 kb, or else which requires 14 kb. So P4 enters, P4 needs 14 kb of free space, fine. So after some time this P1 task completed and we have removed this P1 process. So here 5 kb is left over, and after some time we have removed the P2 process also. Here again the 12 kb is left over. So if P4 process came, so what can we do is, so P4 process, how much memory left over here? So 5 plus 12, fine. Here P1 process we removed and P2 process we removed. So how much space is left? Totally the space left is 16 KB memory is space left over here. But here we need only 14 KB of memory. So can we accommodate this 14 KB of memory over here? No. Why? Because this is not contiguous. So what I mean to say is external fragmentation in the sense, even though we are having 16 KB of memory, but we can't allocate space for the 14 KB for process P4. Why? Because this memory is not in contiguous fashion. So this is known as external fragmentation. So what is a fragmentation? In the sense, leftover spaces, we call it as a fragmentation. There are two types of fragmentations: internal fragmentation and external fragmentation. Internal fragmentation in the sense, whenever we allocated a process to a particular block of memory, partition of memory, in that particular partition, in any memory left over, that we call it as an internal fragmentation. External fragmentation in the sense, among out of this total memory we are having like 16 here, this is what I said is this is 5 KB and this is 12 KB, and here also 2 KB is there. Fine. 12 plus 2 14 and plus 5, totally 19 KB of memory is available over here. But now a process P4 enters which needs 14 KB of memory, but I can't allocate this P4 process to this, even though P4 process requires only 14 KB of memory. But what is the space left with me? 19 KB of memory, which is very much more. Even though I am having the 19 KB of memory, I can't accommodate this P4 process onto this 19 KB of memory. Why? Because this memory is not contiguous. So this is the external fragmentation. I think you have cleared what is an internal fragmentation and external fragmentation. So that is the difference between internal fragmentation and the external fragmentation. Fine. Next one is, it includes a single partition allocation and multi-partition allocation. So we can partition it in a single partition as well as in multi-partition. Here we will be going to have the paging and the segmentation over here. Fine. Here in internal fragmentation, the waste of memory is there, but in external fragmentation there is no wastage of memory. How I will be going to, I mean non-contiguous memory allocation, there is no wastage, that I will be going to tell you. And next one is contiguous memory allocation. Swapped in process are arranged in the original location, but here swapped in process are arranged in wherever the spaces are left at that particular position, these are going to be occupied. So in your syllabus you are having only this contiguous memory allocation. So what do you mean by a contiguous memory allocation? In the sense, contiguous memory allocation is a memory allocation technique. It allows to store the processes only in a contiguous fashion, but not in the non-contiguous fashion. Only in the contiguous fashion only we'll be going to store the processes. Like like as I have said you before, if a block of memory is there, if I want to store P1, in the sense, P1 will be stored over at a single place only. Some half of the P1 here and half of the P1 here will be not going to store like that. So total P1 will be going to store at a particular place only. So that means continuously. That we call it as a contiguous memory allocation. The entire process has to be stored as a single entity. That I mean to say, single entity, we have to store this entire process as a single entity. Next one is static partitioning, or this contiguous memory allocation. Like we'll be going to have two types: static partitioning. Static, we can also say it as a fixed partitioning, or dynamic partitioning, we can say it as a variable partitioning. So static partitioning or dynamic partitioning, so we can say either of the things, static or static or fixed, dynamic or variable. So these are the two memory allocation techniques we will be going to see. The first one is static partitioning or fixed sized partitioning. So what do you mean by static partitioning? Partitioning in the sense, as I have said you before, So listen carefully. As I have said you before, this is the main memory. This is the main memory, and the main memory has been partitioned. This main memory has been partitioned. Partitioned in the sense divided into some amount of blocks. So static partitioning in the sense, this partitioning is there na, like this partitioning. How many partitions are there here? There are three partitions are there. So here this is the one partition, two partition and three partition. These partitions are fixed. These partitions are fixed. We can't include another partition, fourth partition or fifth partition. We can't include. Why? Because before the thing, before runtime only, we will be going to partition the main memory. Fine. Here partitioning in the sense the dividing the memory. Yeah, how many blocks the memory has been divided? Here the memory has been divided into three partitions. The three in the sense static only. If four processors are there and three slots are there, we can't accommodate that fourth processor into the into this memory. Why? Because here the memory has been partitioned into three slots only. How can we accommodate four processes? This partition is nothing but divisions. These are fixed, but the size of the memory can be vary. The size of the partition can differ. This partition may be 2 KB, this partition may be 5 KB, and this partition may be 9 KB. Fine. What I mean to say is partitioning is nothing but division. So how many divisions are there? Three divisions are there. Those three divisions are fixed, but the size of each division can vary. That I mean to say, the first division is of 2 KB, second division is of 5 KB, and third division is of 9 KB. So this is the fixed partitioning. So here this is the oldest and simplest technique. So this memory partitioning is the oldest and the simplest technique used to put more than one process in the main memory. So in order to keep more than one process, we will be going for this static partitioning or a fixed partitioning. So number of partitions in RAM are fixed. Make a note of it. But size of each partition may or may not be the same. It is an optional thing. So here this memory, suppose this is the memory, this memory has been divided into three partitions and another memory is there. This memory is also divided into three partitions. Here what I mean to say is, here the size of first partition is 2 KB, size of second partition is 5 KB, and size of third partition is 9 KB. It may be like this, or size of each partition is fixed 2 KB, 2 KB, 2 KB. Either of the thing we can say. So that is the fixed partitioning. Partitions are fixed and the size of each partition may or may not be the same. So that is very important in this concept. The size of each partition in the sense the first partition, second partition and third partition, the size of each partition may not be the same. So this is the fixed partitioning. So as it is contiguous allocation, here partitions are made before execution or during the system configuration. So before execution only these partitions are done, or before during when we are configuring the system, we will be going to make it as 11 partitions, 12 partitions, like that. Later on we are not at all going to change those partitions. So that is the fixed partitioning. In fixed partitioning we divide the main memory into partitions. So here, as I have said you before, so here the main memory is divided into three partitions. In this main memory, the first partition always allocates to the operating system. As you all know very well, in main memory, one part is going to be occupied by the operating system and rest of the part is going to be used by the user. So one part is going to be occupied by the operating system. Here also, if main memory is there in the sense, here So this is the main memory, and this part is going to be allocated by the operating system. This part is going to be allocated for the user program. So this is the main memory divisions. So one division and second division. First division is going to be taken by the operating system. Second division is going to be taken by the user. In the first partitioning, the operating system is present and the remaining used to store the user. Each partition allowed to store only one process. One process we are going to store in the each and every partition. Degree of multiprogramming is restricted. Why this degree of multiprogramming is restricted? Why? Because here, as I have said you, that here the main memory has been partitioned into 4 partitions. Fine. And now I am having P1, P2, P3, P4 and P5 and P6 processes. Degree of multiprogramming in the sense number of processes when keeping in the main memory. So how many processes we can keep into the main memory. Here, as the main memory has been partitioned into 4, can we keep 5 processes onto the 5 or 6 processes onto the main memory? No. So the degree of multiprogramming is restricted. As main memory is partitioned into 4, we have to keep only 4 processes. Fifth and sixth process has to wait until any one of the process completes its task and coming out of the main memory. Till then the fifth and sixth programs has to wait. So that is the degree of multiprogramming. Every partition is associated with the limit register. So this partition, this first partition, second partition, third and fourth partition. This first partition is associated with a limit register. So this limit register is going to have the lower limit and the upper limit, that is the starting address and the ending address. So this first partition is going to have a limit register. That limit register is going to handle the starting address and ending address of this first partition. Like that, how many partitions are there? For each and every partition, we'll be going to have a limit register. That limit register is used to hold the starting address of that partition as well as the ending address of that partition. This is the fixed sized partitioning diagram. See here. Here what I have said you, how many partitions are there? First partition, second partition, third partition and fourth partition. So fixed size partition. So this we call it as a main memory. This main memory is divided into 4 partitions. So the first partition size is, this block size is 4 MB, second block size is 8 MB, third block size is 8 MB and fourth block size is, so 1, 2, 3, 4. Fourth block size is 16 MB. Here we are having 4 processes, P1, P2, P3 and P4, right? So P1 needs 1 MB, P2 needs 7 MB, P3 needs 7 MB and P4 needs 14 MB of data. But so P1 needs 1 MB, but how much memory, how much block size is there in P1? 4. That means 4 minus 1. That means how much MB left? 3 MB left. P2 has 8 MB size block partition, but P2 needs only 7. That means 8 minus 7. Here 1 MB is left over. And P3 size is 8 MB and P3 needs 7 MB. Here also 8 minus 7, that is 1 MB is left over, and P4 needs 14. P4 block size is 16 MB and P4 needs only 14 MB. That means 16 minus 14, that is 2 MB is left over. So how much space is left over? 3 plus 1 4, 4 plus 1 5, 5 plus 2 7 MB is left over. This 7 MB, so leftover spaces here, out of 4 MB, this is of 4 MB, we have used only 1 MB, 3 MB is left over. Out of 8 we have been used 7 MB, 1 MB is left over. Out of 8 we used 7 MB, 1 MB is left over. Out of 16 we used 14 MB, here 2 MB is left over. This leftover spaces, these all leftover spaces, what we call it as an internal fragmentation. Got it? That leftover spaces we call it as an internal fragmentation. So I'll be telling you the external fragmentation also. Now suppose a P5 process came. P5 process came. This P5 process needs 6 MB of space. P5 process needs 6 MB of space. Totally how much memory left over with me? Leftover memory is 7 MB. But P5 needs only 6 MB. Can I allocate this P5 onto the leftover spaces? No. Why? Because all the leftover spaces are not contiguous. So here 1 MB, here 1 MB, 2 MB, like that. It was not contiguous, so that even though I am having 7 MB of free space, this P5 needs only 6 MB, but still I can't accommodate this P5 process onto this leftover space. Why? Because that leftover space is not contiguous. This we call it as an external fragmentation. Even though we are having the memory of 7 MB, but we can't accommodate 6 MB over here. Why? Because it is not contiguous. So that is the external fragmentation. Fine. So here as I explained you there, so the theory over here. Fine. Here 7 MB has been left over here, but if a P5 process of 7 MB comes, 7 MB memory space is left over here, and P5 process came which requires 7 MB, but we can't accommodate this P5 process onto the leftover space. Why? Because this is not contiguous, because of contiguous memory allocation. So hence 7 MB becomes the external fragmentation. Even though the memory is there, we are not unable to keep the process, allocate the process onto the leftover memory. That we call it as an external fragmentation. So what are the advantages of fixed partitioning? So if we are going to divide the memory into fixed partitions, that means constant, the 1 2 3 4 partitions, in the sense these are fixed. So what is the advantage of it? Easy to implement. Why? Because if process P1 is there, the whole total process we will be going to allocate at a single place only, at a single place. So easy to implement, little operating system overhead. Overhead in the sense operating system can't check for different places where that P1 has been stored. Why? Because we are storing all the P1 at a single space only. So that is the advantage. Disadvantage is internal fragmentation, that as I've said you, leftover spaces. External fragmentation is also there. Why? Because that leftover spaces we can't allocate to another process. So that is external fragmentation. Limit process size. Limit process size in the sense, if processes are 5 processes but the memory partitions are of 4, so we can't allocate the 5th processor onto the memory. Why? Because here the memory, for a memory partition there is a limit. So that is the drawback of fixed sized partitioning. And limitation on degree of multiprogramming. As I have said you before, degree of multiprogramming in the sense keeping the number of processes onto the main memory has been reduced. Why? Because here the memory partitions are fixed. We can't change the number. We can't increase the number of partitions, as well as we can't decrease the number of partitions. Why? Because at that time of you will be going to have during the system configuration, only we will be going to fix the size of the partitions, or before execution only we will be going to fix the size of partitions. So that is of fixed sized partitioning. And another thing is variable sized partitioning, or we can say it as an dynamic partitioning. variable size or dynamic partitioning. Dynamic in the sense, suppose here the memory is there in the sense, dynamic partitioning in the sense, suppose here there is no fixed size of memory, so this is the main memory. So process P1 came, which requires 3 KB of data. So here this process P1 is allocated, here 3 KB of partition we will be going to keep. Process P2, which requires 12 KB in the sense, here we will be going to keep process P2, which we will be going to have 12 KB. And process P3 came, which requires 16 KB in the sense, here process P3 we will be keeping, and here 16 KB we will be keeping. So here process number of processes is equals to the number of partitions here. There is no restriction in the partitions. Fine. During the runtime we will be going to allocate the memory, but there during that before runtime only, during that before runtime only we will be going to fix the partitions. But here during the runtime, how much processor, if I needs 5 KB of memory, 5 KB of memory we will be going to occupy. So here what will happen, here we don't have internal fragmentation. Why? Because there is no space left over. So P1 needs 3 KB in the sense we are going to keep 3 KB only. P2 needs 12 KB in the sense we are giving 12 KB only. P3 needs 16 KB in the sense we are allocating 16 KB only. We are not allocating 18 KB or 20 KB like that. How much the process are in required of, that much amount of memory only we are allocating. So here totally we are removing the internal fragmentation. Got it? So here various features associated with variable partition are, initially RAM is empty. So initially here the RAM, the main memory is empty. So this is empty one initially. So during the runtime, according to the processor needs, instead of partitioning during the system configuration. So when it comes to the fixed partitioning, the partitions have done during the system configuration itself. But here during the runtime, suppose if process P1 came, P1 says that I need 5 KB of memory. So here we will be going to make a partition of 5 KB for P1, and process P2 came. P2 say I needs 8 KB of memory. So we'll be going to do another partition 8 KB for P2. Like this, runtime we are going to do the partitions of the memory. So here we are completely eliminating the internal fragmentation. The partition size, see here, the partition size varies according to the need of the process. Here this process needs 5 KB of memory, this process need 8 KB of memory. So during the according to the need of the processes, we are making the partitions to avoid so internal fragmentation is completely avoided, and to ensure efficient utilization of the main memory. So that is why we are going for fixed size partition to variable size partition. In olden days that fixed size partition is going to be used, but nowadays like we are going for the variable sized partition only. Next one, number of partitions in RAM is not fixed and depends on the number of incoming process. So based on the incoming processes only the memory is going to be partitioned. So during the system configuration we are not processing, at the runtime we are processing the memory. So that is the advantage of having the dynamic memory allocation or dynamic partitioning, or we'll be going to say it as a variable partitioning. Fine. So if you see the example here, the main thing you have to keep in mind is here the partition size is equals to the process size. So here the block, here the process P2 needs 2 MB. So here the partition is also 2 MB. Process P2 needs 7 MB. The partition is also 7 MB. P3 needs 1 MB. Here the partition is also 1 MB. Likewise, so the necessity of the processor is equals to the size of the partition. So that's why we are completely, what we are doing, eliminating or reducing the internal fragmentation. So this is internal fragmentation. This is the important thing we have to keep in mind in variable or dynamic partitioning. In dynamic partitioning, we don't have internal fragmentation. Fine. So what are the advantages? The first and the foremost thing is no internal fragmentation. Why? Because the process size is equals to the partition size. So no degree of multiprogramming. Why? Because we are not keeping restrictions to number of partitions. So how many processes are coming, those many memory allocations we are doing. So there is no degree of multiprogramming and no limitation on the size of the process. So the process size is also, there is no limitation, only 10 process has to come, 11 process has to come. There is no such sort of like that. So here in fixed partitioning, the processor with the size greater than the size of the largest partition could not be loaded and processor cannot be divided. It is an invalid in contiguous location. Why? Because here the process, the partition, here the memory size is of 20 KB. If a processor needs 26 KB, can we allocate? No. Here the memory itself is a 20 KB. How can we give 26 KB? So it is an invalid partitioning. So these are the advantages of fixed, dynamic partitioning or variable partitioning. What are the disadvantages? It is very difficult to implement. Why it is very difficult to implement? In the sense, here it involves allocation of memory during the runtime rather than system configuration. So during the runtime, like we don't know which process needs how much amount of memory. So that's why it is a bit headache to the operating system. External fragmentation. So there will be an external fragmentation in spite of absence of internal fragmentation. So as there is no internal fragmentation, external fragmentation in the sense, suppose here as I have said you, here 1 KB is filled, 2 KB is filled and 6 KB is filled. Here 2 KB is free and here 5 KB is free. Totally 7 KB is free. Suppose if a process P1 comes which requires 7 KB, in the sense I can't allocate this and this over here. Why? Because it is not contiguous. So this is how we will be going to say that there is an external fragmentation in the dynamic or variable sized partitioning. So external fragmentation is found in a variable partitioning scheme. To overcome this problem, we will be going to use a technique called compaction. What do you mean by compaction? In the sense, like in the external fragmentation, what we have done, so all the spaces are left over in the middle. Here one space is left over, here two spaces left over. So here 5 KB and here 2 KB is left over. So what we are going to do is we are compacting all those spaces. Compacting in the sense, we are keeping that 5 KB and 2 KB at even either at the ending or either at the starting. We are grouping all those spaces and keeping those spaces at the end or at the top, so that it will be used by the another process. So if P1 came 7 KB, in the sense, okay, now this 7 KB is totally free, 5 plus 2 7 KB is free. Now I can allocate to this P1 process. But here previously, here 5 KB is left over, here 2 KB is left over, which is not contiguous, so that I can't allocate the process P1 over here. But when I do the concept of compaction, compaction is nothing but bringing all the spaces together either at the top or either at the bottom, so that 5 plus 2 becomes a 7 KB of space is left over, so that now I can give this process P1 to this 7 KB of space. So that is the compaction. Fine. See here, so fragmented memory. So here one space is left, suppose here 2 KB, suppose here 5 KB, here 1 KB, here 2 KB. So 2, 3, 5 plus 5. So totally 10 KB of space is left over. If a process P1 comes with 10 KB, should I accommodate this process P1 over this leftover spaces? No. Why? Because not contiguous. They are not contiguous. Now what I am doing is, now I am doing the concept of compaction. I am getting all the spaces, whatever the spaces are there, I am bringing all the spaces together to one point so that it totally becomes a 10 kb. Now if a process P1 needs a 10 kb, I can accommodate that process P1 over here which requires 10 kb. So this is the process of compaction. Fine. So in order to overcome that drawback, external fragmentation, not internal fragmentation, in order to overcome that external fragmentation, what that leftover spaces are bringing either to the starting or either to the ending in order to have the huge space so that it can be utilized by the another process. So that is the technique used by the compaction. So this is how the contiguous memory allocation is going to be done. So in contiguous memory allocation we are having fixed size partitioning and variable size partitioning. Fine. So in fixed size partitioning we are having the internal fragmentation, and in variable size partitioning we are having the external fragmentation. Internal fragmentation in the sense the leftover spaces, external fragmentation in the sense in the whole memory whatever the leftover spaces, we call it as an external fragmentation. That external fragmentation can be overcome by making use of compaction. Fine. This is how the internal fragmentation and external fragmentation is going to be done in the contiguous memory allocation. There is non-contiguous memory allocation is not there in your syllabus. So we are having only contiguous memory allocation. In that contiguous we are having a fixed and variable size. In the next class what we will be going to do is, we will be going to see the memory allocation algorithms for both the fixed and the variable size. There are 4 different algorithms: first fit, best fit, next fit, worst fit. These are the 4 memory allocation algorithms, and these algorithms we'll be going to see in the next class. Thank you, students. Like when we are going for this memory allocation algorithms, like you will be going to see which algorithm is best. So by making use of this first, best, worst and next algorithms, we will be going to select the best one. Fine. Thank you, students. That's all for this today's class. Have a great day.